All right, we got our first lesson for 2.3. So again, I'm going to play a little bit here from Mr. Martin for examples 1 through 5, and then I'm going to take over for the last 3. So let me give you the
Then
first
you
part.
just take the derivative of each function separately and add them together, sum or difference, that works. So for example, if you were to take the derivative of this thing down here in the black, then you would take the derivative of this minus the derivative of this plus the derivative of this and treat each term differently. Well, that doesn't work with products and quotients. A few people tried to do that in their assignment for that, and we found that that doesn't work. So we fall back on the product rule. The product rule, you can see up here in the green, it says the derivative of f of x times g of x is, we call this the first function and this the second function. So the way we want to write this up then is the derivative of the product is the first times the derivative of the second plus the second times the derivative of the first. And you can do this in any order. You can mix these up because multiplication commutes and so does addition. So you could do the first times the derivative of the second plus the second times the derivative of the first, or switch that order. But either way, here's what this would look like. Here on this one, if we did it this way, we would get, if we treat this function like it's the first, this function like it's the second, then we do first times the derivative of the second. So what does that look like? Well, there's the first, and now we multiply that times the derivative of the second. What's the derivative of this? 3x squared only. So that's going to be this part right there. And then if you check out up here what we've got, plus, so we're going to add that product to, and now we're going to do the second function times the derivative of the first, so it's going to be this whole thing here, okay, times the derivative of the first. The derivative of this function on its own is 2x minus 2, and so when you multiply this out, you'll have to distribute. Okay, you get 3x squared times each of these terms gives you these 3 terms. When you FOIL on these binomials, you get this, and then you clean it up and put it into standard form, combine the like terms, and you get whatever you get. Notice if you did this same exact problem by first distributing the f of x, and you multiplied x cubed times all 3 of these, and then minus 1 times all 3 of these, and then came out with a 6-term polynomial that you might be able to combine like terms on, and then if you differentiate that, you would get the same thing as you get right here. Okay, so for something like this, there's not 2 different ways to do it. Up here in example 1, you could distribute first and then differentiate, or differentiate with the product rule and then distribute and combine like terms. Down here, for this one, there's not 2 ways to do it. You have to use the product rule. We're going to treat the first function like it's x. The second function is cosine of x. So what's our rule? First times the derivative of the second plus second times the derivative of the first. So there's the first. Derivative of the second, what's the derivative of cosine? Negative sine. Plus, and now we do second times the derivative of the first. Second is cosine of x times the derivative of the first, which is just 1. And so you get whatever you get in this case. It is negative sine of x plus cosine of x. Okay. For example 3, let's go ahead and take a look at example the example on the bottom of page 114 in your text for use of the product rule with 3 different factors. That's a great example. If you have one function times a second function times a second function, it shows you there how to handle that. It's basically you just do the product rule several different times. So you can follow that if you encounter that. For the quotient rule, the derivative of a quotient has a very different look that we're going to do. When we have the derivative of f of x divided by g of x, it's not the derivative of the numerator divided by the derivative of the denominator. It doesn't work like that. It has a very unique formula to it. And so what we do is, for the numerator here, we're going to do the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So if we call this the high, as in the one that's higher out of these 2, and this the low out of, which means it's the lower out of the 2, the high and the lower, the numerator and denominator, then a way that is very common for most teachers will teach it this way. It's a little saying to help you remember this. The derivative of a quotient is low d high minus high d low over low squared. Say it again. Low d high minus high d low over low squared. What does that mean? The low means the denominator, times the d high means the derivative of the numerator, minus the high, which is the numerator, times d low, which is the derivative of the denominator, over low squared, which is the denominator squared. So that's the same for it. You'll remember it and use it. Everybody does, and that's it. So for this one here, it's not just the derivative of this rational function is not just going to be 2 with the derivative of the top divided by 1 the derivative of the bottom, so the derivative is 2 everywhere. That's not the case. It's not linear. So instead we have to apply this property. So what's it going to be? What goes first? We've got low d high minus high d low. So what goes first? The low, which is this, times the derivative of the high, which is 2. So it's going to be x plus 1 times 2 to start out. And then, so we'll get that on top. Okay, and then over here we get minus high d low, so minus the entire numerator times d low, which is just 1. So then that's going to be minus, and make sure you put everything in parentheses so this minus sign distributes. So it's minus the numerator times the derivative of the denominator minus high d low over low squared. And guys, we want to keep things factored as much as possible. Sometimes things will cancel out. A lot of times it does. A lot of times the quotient rule is pretty ugly, and it starts out ugly but then cleans up pretty nice at the end. Sometimes it does, sometimes it doesn't. So now nothing cancels here, so we can distribute and see if there's anything that cancels later on. Then 2x's cancel out, so we get just a 5 over the quantity x squared plus 1 quantity squared. Sometimes we want to take techniques, and a lot of times you're going to have a choice on which technique to use. Sometimes one is just as good as the other in this class. Sometimes one is definitely quicker than others. So in example 5 here, you could do the quotient rule on this whole thing. You could do low d high minus high d low over low squared and then clean it up. You definitely could do that, but quotient rule is usually our last resort. It's the longest steps to a process. So if you can do anything to this to turn it into a sum or difference rule instead of a quotient rule, then that's what we want to do. So notice, since both of these terms have the same denominator, we can rewrite them each with the same denominator. So think of this as 7x cubed over 2x, which cancels out to become 7 halves x squared, and then the minus 8x squared over 2x becomes minus 4x. And now this is much easier. It's always easier to differentiate a sum or difference than it is a product or quotient. So if you can change the form of it first, that's just a huge deal in this class. We want to simplify and get it into a friendly form first before we do any calculus. That's really the mantra in the class moving forward from here. So now we differentiate and we get whatever we get. In this case, y prime is 7x minus 4.
All right, let me give you 3 more examples here. So example 6 is just on the next page in your notes. If you flip that page, so again, we're going to do a derivative. You can see right here we have another quotient rule. So again, we're going to do the whole low d high minus high d low. I just wanted you to see a couple with some of more of our trig functions. So just remember, derivative of cosine we know is negative sine. Derivative of e to the x is e to the x. And so this is, again, just the low times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then we're just going to simplify that as much as we can. On top, I factored out the 2e to the x, and that looked like this. And the reason we did that, of course, is because you can see how that would cancel with one of those factors on bottom. And so that cancels this guy, and it drops this to a first power. And that's just as simple as that one's going to get. And earlier in the video, he mentioned what it would look like if you had 3 factors. So I'm not going to distribute all this, but I wanted you to at least see what that would look like. So if we were going to do the derivative of f of x, and these were the 3 factors, here's the general rule that we're going to apply here. So it's the derivative of the first times the second 2, on and on, as you can see how this goes. So each one is going to get a derivative in there. You got your h function there and your k function right there. That's your third factor. And so if we lay that out, this is that big, long, whole line would be how that would look if you put it into that formula right there. So, and then from here, you would just have, and I didn't want to simplify it all, so I'm just going to say at this point, you got a whole lot of distribution that you would have to do on that if you wanted to simplify it. Combine like terms, and we would just clean it up as far as we could possibly take it. But I at least wanted you to see how that would work if you had 3 factors instead of 2. All right, so you can see the layout right there. And one last case to show you. 2 last cases, sorry. So for example 8, so we're given the graph of 2 functions. So this is our graph for f, and this is our graph for g. And we are asked to find the derivative of graph P, which is the product of those two functions, where x equals 1. And so all we're really applying on this is the same product rule, and we're just going to get the derivative information right off these graphs. Okay, so if you think of p of x as the product of those two, again, we're going to do the first times the derivative of the second plus the second times the derivative of the first. And this information we're just getting right off of the graph. So if we said f of x, right, and so I'm looking for all these, we're looking where x is 1. So that's getting plugged in for those guys. So I need to figure out what is f of 1, what is g prime of 1, on and on, as we plug in those ones for x. And then as we look at the graph, so we'd say, well, what's f of 1? So here's my f function. If I go to where f is 1, I can see that the y coordinate is 5. So that's getting subbed in for him. The derivative of g, where x is 1. I'm going to take a look at this guy. So when you think derivative, you got to think slope, right? So if I'm trying to figure out what is the slope at this point, well, this is a line. And in a line, the slope is constant no matter what point you're at. So if I just find the slope of this line, I have the derivative of any point on this line, right? And so if you look right here, I can just count rise over run. So if I go up 2 over 1, I can see that the slope of this line is 2. So where x equals 1, where x equals any of these points, I can fill that in with a slope of 2, right? And so that's where that 2 is coming from. And then we're going to say, what's g of 1? So I can see I have the point 1, 1. So that's where this guy comes from. And then again, for the slope of the f function where x is 1, so here's where x is 1. So again, because it's a line, I just need the slope of this line, right? So this one is going to go down 1 over 1. So the slope at any point on this line would be negative 1. And so we can fill that in, and once we clean it up, we got a result. Okay, here's the last one. Get all that on there for you. So we have basic formula for area of a triangle, 1/2 base times height, but we are given the base and the height in terms of time, right? And so that's our t, represents time on this one. And so if we did 1/2 the base times the height, we get this look right here. And so that's the function that we're working with. And we're told that our area is our a function, and then that t again represents time. So we are asked to find the rate of change of the area, our y value, with respect to x, which is time. So dA over dt, right? That's just like saying dy over dx. And so because of this, first of all, we can pull out, you could distribute the 1/2 if you wanted to, or you can just pull it out as our leading term. And so we can separate out that 1/2 and then do the derivative on these two functions. So just throwing these into our product rule. So you got your first times the derivative of the second, plus the second times the derivative of the first. And then we just always simplify as far as we can. So because that's just a single term, we can just distribute it to this first factor. And that's where this comes from. And then on this part, we're just multiplying those two together to get this. And then we're just simplifying whatever we can from there. And that's it for part 1.